हेलो ऑल, वेलकम टू दिस चैनल। माय नेम इज विनय कुमार फ्रॉम द गेट मैकेनिकल टीम ऑफ पीडब्ल्यू। एंड इस वीडियो में मैं आपको आइगन वैल्यूज एंड आइगन वेक्टर्स का थोड़ा सा डिटेल्ड डिस्कशन करता हूं। सो नाउ इफ यू सी दिस आइगन वैल्यूज एंड आइगन वेक्टर्स, सो पहले हम वेक्टर्स के बारे में कुछ 2-3 पॉइंट्स देखेंगे। सो वेक्टर्स, इफ यू सी, normally might have studied, normally if I take one vector I plus 2j, for example, okay, or I plus j, simple vector let us take initially. If you take I plus j, so मान लो कि it's a vector in 2-dimensional space. So if you plot this, you know, in a Cartesian coordinate system, if you plot this in a Cartesian coordinate system, so this is Eigen, ये होता है कि x axis, y axis, and the point 1, 1 is somewhere here. Okay, so this point is 1, 1. So हम वेक्टर्स कैसे प्लॉट करते हैं? So 0, 0 से स्टार्ट करके ये पॉइंट तक 1, 1. So let us take this as point A. So this vector I plus j is actually this vector I bar plus j bar. Okay, so इस वेक्टर को हम पॉइंट्स में लिखते हैं 1, 1. Similarly, if the vector is in 3-dimensional, you will write the 3-dimensional point. Like for example, I plus 2j plus 3k, तो पॉइंट होता है कि 1, 2, 3. Okay, so इस पॉइंट को हम जनरली कॉलम वेक्टर से भी डिनोट करते हैं 1 and 1 like this. Okay, so this is a vector actually, and it's not a unit vector. इसका लेंथ 1 यूनिट नहीं है। अगर आपने इसका लेंथ कैलकुलेट किया तो it is square root of 2. So this is not a unit vector. So we know that if this is along the x-axis, if you take this as I bar, for example, so just a minute, if you take this as I bar, for example, like this is a unit vector on x-axis, and if this is a unit vector on y-axis, which is j, so normally हम इस unit vectors को I and j से डिनोट करते हैं. Okay, so that's the vector. So normally, so you can plot vectors in any 2-dimension or 3-dimensional spaces. Now vectors में हम basically दो transformations करते हैं. So if you see basic transformations on vector, हम basically vectors में दो transformations करते हैं. ये होता है कि scaling of vectors, scaling of vectors. So scaling में हम क्या करते हैं? Vectors का length बदलते हैं. Okay, so length is changed. लेंथ इज चेंज्ड एक्चुअली. ओके, सो हम वेक्टर्स का लेंथ बदलते हैं. एंड दूसरा ट्रांसफॉर्मेशन ये होता है कि रोटेशन ऑफ वेक्टर्स, रोटेशन ऑफ वेक्टर्स, रोटेशन ऑफ वेक्टर्स. सो इसमें हम क्या करते हैं? वेक्टर्स का डायरेक्शन मींस मतलब ओरिएंटेशन चेंज करते हैं, है ना. सो ओरिएंटेशन इज चेंज्ड, ओरिएंटेशन इज चेंज्ड. लाइक, so if you see this, for example, हमने उस वेक्टर को देखा तो 1, 1. okay, so 1, 1. अगर आपने देखा तो Eigen x y, for example, and मान लो कि ये वेक्टर is 1, 1. okay, so let me take that. Fine, so if you see this is 1, 1, 1, 1, and इस पॉइंट को हमने ये से डिनोट किया था. नाउ स्केलिंग हम ऐसे करते हैं कि अगर आपने इस वेक्टर लिया तो 1, 1, then if you apply some transformation on this matrix, so ये होता है कि 2/1. so let us suppose if you apply some transformation with a matrix A B C D, इसका रिजल्ट ऐसे आता है कि मे बी 2, 2 or maybe 3, 3, 4, 4, 5, 5, anything it can happen. Okay, so that's why basically this comes out as some constant times of 1, 1 actually. Okay, so is होता है कि 1, 1. So basically if you plot this point k, k, for example, k is equal to 3, for example. Okay, for example I am taking k is equal to 3. So what's the meaning of that? आपने जब इस मैट्रिक्स को इस वेक्टर में ऑपरेट किया तो this vector 1, 1 changes as this vector 3, 3 actually here. Okay, so this vector changes 3, 3, maybe somewhere here like this. Okay, so this vector is 3, 3, 3, 3, and this is point B. So what happened here is initially the vector is OA, so इस OA को हम OB से बदल दिया. Okay, so this vector's direction is not changed, but the length of the vector is actually changed. So I say matrices को we'll call them as scaling matrices, scaling matrices, or generally अगर ऐसे मैट्रिक्स को किसी वेक्टर मिला तो वी कॉल देम एज स्केलिंग वेक्टर्स और वी विल कॉल देम स्केलिंग वेक्टर्स. सो दूसरा ऑपरेशन ये होता है कि रोटेशन ऑफ वेक्टर्स. रोटेशन ऑफ वेक्टर्स हमने स्केलिंग देखा था. सो स्केलिंग में क्या होता है? सो व्हेन यू अप्लाई दिस ट्रांसफॉर्मेशन, दिस वेक्टर विल चेंज इट्स लेंथ, बट इट मे चेंज इट्स डायरेक्शन बट अलोंग द सेम लाइन. ओके, बट इट वोंट गेट रोटेटेड. बट नाउ इफ यू सी रोटेशन ऑफ वेक्टर्स, अगर आपने रोटेशन ऑफ वेक्टर्स देखा तो सो इसमें क्या हो जाएगा? आपने इस एक्स वाई कोऑर्डिनेट सिस्टम लिया, ऑरिजिन एक्स वाई, and now if you take the same vector 1 comma 1, for example, say somewhere here, it's decently good to take some point here. So 1 comma 1. Now this point is A and आपने ये vector OA, like as usual, if you plot this vector OA, now कुछ मैट्रिसेस ऐसे कहता है कि अगर आपने इस 1 comma 1 में इस ट्रांसफॉर्मेशन अप्लाई किया तो ए बी सी डी, रिजल्ट ऐसा आता है कि -1 comma 1. -1 comma 1 का स्पेशलिटी क्या होता है? लुक, इफ दिस इज वेक्टर 1 comma 1 i plus j, इफ दिस इज i plus j, अगर आपने इस वेक्टर को 90 डिग्री रोटेट किया तो आपका वेक्टर कैसा आएगा? योर वेक्टर गेट्स कन्वर्टेड टू दिस पर्टिकुलर ओरिएंटेशन, है ना? So this is how you get the vector. If you rotate this by 90 degrees actually, so if you rotate this by 90 degrees, then if this point you call B, इसका पॉइंट का कोऑर्डिनेट्स होता है कि -1 comma 1 and ये वेक्टर होता है कि -i plus j. मतलब you can see this vector got rotated by 90 degrees when you apply this transformation, and these matrices are called rotation matrices. Rotation matrices. For example, if you want to calculate what is this matrix, okay, so see, I'm calculating. So if you multiply these two matrices, you will get A plus B, C plus D is equal to -1 and 1. So any four values which satisfy this condition, okay, so A into 1 plus B into 1, actually C into 1 plus D into 1 is equal to -1 comma 1 actually here, okay? Or else if you take the generalized point, let us suppose if this is a point on the line y equal to x, so let us suppose if you take x and y to denote the point, now this point is getting transformed as, if the point is on line x comma y, means y is equal to x. So if this line is y is equal to x, you know this line is going to be y equal to -x. This angle is 90 between them, okay? So this angle is 90, so this point gets converted to -x comma y, correct? अगर ये y equal to x में y equal to x लाइन में पॉइंट हुआ तो आफ्टर ट्रांसफॉर्मेशन दिस पॉइंट y equal to -x में जाएगा, करेक्ट? सो दैट्स व्हाई दिस ट्रांसफॉर्मेशन इज -x comma y. सो इफ यू नाउ डू द मल्टीप्लिकेशन टू गेट द जनरल 90 डिग्री रोटेशन मैट्रिक्स, आपको a आएगा कि ax plus by cx plus dy is equal to -x comma y. सो अगर आपने ये दोनों एलिमेंट्स कंपेयर किया तो बिकॉज बोथ द मैट्रिसेस आर सेम, सो A, B, C, D, इसका वैल्यूज क्या होता है? इफ ax plus by is equal to -x, A का वैल्यू होता है कि -1 and B का वैल्यू 0. सिमिलरली C का वैल्यू cx plus dy is equal to y, so C का वैल्यू होता है कि 0 and this is 1. So this matrix is called a rotation matrix which rotates the any point by 90 degrees actually here, okay, on this line. But eigenvectors is all about this scaling, okay? So मान लो कि अगर इस वेक्टर का स्केलिंग मैट्रिक्स है तो now when you apply this transformation of this matrix on this vector, only the direction, only the magnitude of the vector is changing, only the length of the vector is changing, direction is not changing. That means this transformation can only change the length of this particular matrix or the length of this particular vector, but it cannot change the direction. So that vectors corresponding to any given matrix are called eigenvectors. So now if you see, what we'll talk about eigenvalues and eigenvectors is when you take any matrix, for example, A is a n by n matrix, for example, okay? So let us suppose this A is an n by n matrix. Now whenever A is an n by n matrix, when A is an n by n matrix or is an x, y, for example. So let us suppose this is a vector x in this direction, okay? So let us suppose this is a vector x bar, for example, something like this, x bar and this point is, let us say, x comma y, for example here. Then a into x, let us suppose if this is the vector a into x bar. So x bar is normally some column vector which we write. So let us suppose this x is actually a n by 1 vector and this a is a n by n matrix. So when you perform this transformation, when you perform this multiplication, what you get actually, you will get as some lambda times of x bar, which is also of size n by 1 again, because when you multiply two matrices of size n by n and n by 1, but these two are denoting vectors. Okay, and whenever x bar is a vector, if lambda is a constant, okay, so where lambda is constant. Now whenever lambda is a constant, if you multiply some constant to this vector, this term will actually give you only the change in length of that vector. Correct? Means let us suppose if lambda is equal to 2, for example, if lambda is equal to 2, then if this is x bar, then how will be 2x bar? 2x bar will be something like this. Correct? So 2x bar will be something like this. 2x bar. If lambda is equal to 3, for example, if lambda is equal to 1 by 2, for example, okay, so then this direction will be something like this. This will be something only half of this x actually in that case. Okay, so this is half x bar. Similarly, if lambda is equal to -1, along the same line, just the direction changes to the opposite sense. Okay, so this particular combination means when you apply this matrix on this vector, only the length of the vector changes, but the direction does not change, because 2x and 3x or 1 by 2x minus x all will be along the same line of action and their direction will be same. So now if you see this equation, we have ax bar minus lambda x bar is equal to 0. So this can be written as a minus lambda times of I multiplied on x, because if you want to multiply two matrices, this can be written as I into x. So I am taking out is equal to 0 bar. Now आप सबको पता है अगर हमारे पास एक linear system है तो let us suppose this is a linear system of equations. Okay, then for this equation y equal to 0 is always a solution. Okay, मतलब मान लो कि a 4 by 4 equation with 4 unknowns and 4 equations, then for y is equal to this vector 0 0 0 0, this equation always gets satisfied, but there will be other solutions of this equation at which this equation is satisfied. And now if you see, for not having a trivial solution means for y to have other values apart from these zeros, that b should be 0 actually. Okay, so a चीज हम system of equations से पढ़ते हैं. So for this system to have non-trivial solution, मतलब 0 से बिना अगर कुछ solution होना तो this determinant of b should be definitely 0 actually in this case. Okay, so that's why using this point of consistency of equations, if you want to have this x bar, means if you want to have some particular directions for this given matrix, definitely this coefficient should be 0. Okay, so means coefficient determinant should be 0. For non-zero, for existence of non-zero x bar, for existence of non-zero x bar, definitely the coefficient of a minus lambda I should be 0 actually here. That's how the characteristic equation gets generated for this given system. And the equation that of a minus lambda I is equal to 0 is called characteristic equation. Characteristic equation of a n by n. So when you solve this equation, we get eigenvalues. So solving that a minus lambda I is equal to 0, this will be a polynomial equation, and this gives us eigenvalues. Give eigenvalues. So eigenvalues are nothing but scaling factors. Means in a particular direction, if you apply the transformation, by what amount this lambda or this matrix will change the length of that vector, that is decided by this lambda. And so basically this gives you the eigenvalues. Okay, so now let me explain you a bit more about this eigenvalues and eigenvectors with an example. Okay, so let us suppose if you take an example, for example a is equal to, I am explaining you with 2 by 2 size so that I can show you things geometrically, then we can extend for 3 by 3 using the same identity. So 1 2 2 1, for example. Okay, I am taking a simple 2 by 2 matrix. Now, if you consider this equation for this matrix, this implies A minus lambda I is equal to 1, 2, 2, 1 minus lambda 0, 0 lambda is what you get. So this is equal to 1 minus lambda 2, 2, 1 minus lambda actually. Okay, now if you simplify this, det of 1 minus or det of A minus lambda I is equal to det of 1 minus lambda 2, 2, 1 minus lambda is equal to 0. So if you simplify this, this is just determinant calculation. What I'm doing is equal to 0. This can be written as lambda minus 1 square minus 4 is equal to 0. So lambda square minus 2 lambda plus 1 minus 4. So minus 3 is equal to 0. So lambda is equal to 3 comma minus 1. So these are the correct. So sum should be 2. So 3 comma minus 1 are the roots of this equation. Now what does this 3 and minus 1 tell to you? Okay, so by looking at this equation, हमको क्या पता चलेगा? Let us see this. So first, for lambda is equal to 3. Now what is the meaning of this lambda is equal to 3? We identify such vectors जिन vectors में अगर आपने इस ट्रांसफॉर्मेशन किया तो मतलब इस वेक्टर है हमारे पास, and if you are doing this transformation, the length of this vector changes by 3 times. Okay, so 3 times of x हो जाएगा. Okay, so that's what this lambda actually tells you. So if there is a vector, if you apply this transformation A on this vector, then this transformation will create the 3 times vector of this particular vector actually. Okay, so now if you see this, let us apply our definition. Ax is equal to lambda x. So whenever you take these points 1, 2, 2, 1, x, y, because you are dealing in points, so lambda which is 3, so 3 times of x and 3y actually here, correct? So if you simplify this, this implies x plus 2y and 2x plus y is equal to 3x 3y, 3x 3y. So this implies, if you simplify, x plus 2y is equal to 3x. So this implies y is equal to x from this equation. And from second equation, what do you understand? 2x plus y is equal to 3y. So in this equation also x is equal to y. Means you understood that this vector x bar which you have initially taken xy is in that particular direction where x is equal to y. So if you replace y with x, then by taking this x out, you get 1, 1. So this 1 comma 1 is an eigenvector of this matrix corresponding to this eigenvalue. What is the physical meaning of this? You got 3 things here. Look, I'll actually explain you. So see here, let me explain you here. Okay, before that I'll erase this. Okay, so see here. We'll see practical applications a bit later, but let me explain you what is the geometrical meaning of these 3 quantities that you got. So first thing, you have the matrix which is 1, 2, 2, 1. Then you got one eigenvalue lambda 3, and corresponding to this eigenvalue you got one eigenvector 1, 1. So what is the meaning of these 3 things? Look, when you take this xy coordinate system, origin x, y, if you take any vector in this direction, so let us suppose if you know y is equal to x line is something like this. So y is equal to x line is something like this, for example. So y is equal to x is something like this. Now when this is y is equal to x line, if you take a vector 1 comma 1, for example, means if you take a vector 1 comma 1 like this, if you take a vector 1 comma 1 like this, then what happens? When you apply this transformation on this vector, this is x. When you apply this transformation, if you multiply this matrix with this matrix, the result will be 3 and 3. Okay, so 3 comma 3 point will be somewhere here. So the transformation gives you this new vector like this. actually here. Okay, so this is 3 comma 3. Means basically you can see if you multiply these two, you will get 1 plus 2, 3, and 2 plus 1 again 3 is what you will get. Okay, so that means the transformation of this matrix on this vector will give you a change in the length of that particular vector. Then we call this is the eigenvector of this matrix. Similarly, you take any vector in this direction. For example, you take 2 comma 2 somewhere here. If you take 2 comma 2 point here, if you take 2 comma 2 point, or okay, 2 comma 2 point you take, for example, somewhere here. If you take this point 2 comma 2, okay, so if you take this vector 2 comma 2, for example, if you take this vector 2 comma 2, and if we apply transformation of this matrix on 2 comma 2, the result will be 6 comma 6 actually. Okay, so you can see here, this will create the vector which is 6 comma 6, which is 3 times of this particular vector actually. Okay, so this will create a vector which is 6 comma 6 somewhere here. This is 6 comma 6. So you take any direction, definitely this vector, when you apply on this particular matrix which is along this particular direction, this matrix for this particular eigenvalue will convert the length into 3 times. Okay, so this a into x will give you 3 times of x when this x bar is along the direction y is equal to x. So this is the meaning of eigenvector actually. These three are connected in such a way that when you apply this matrix on this vector, this length of the vector changes by 3. Okay, when you consider 1 comma 1, this gives you 3 comma 3 vector. When you consider 2 comma 2, it gives you 6 comma 6. If you take 4 comma 4, it gives you 12 comma 12. Okay, so like that, this eigenvector will actually convert this. Okay, so this is how we calculate the eigenvalues and eigenvectors correspondingly, and these eigenvalues and eigenvectors are very much important in our practical applications as well. How do you see? Let us suppose आप सबको पता है किसी ने स्ट्रेंथ ऑफ मटेरियल्स, फ्लूइड मैकेनिक्स, अगर ये सब्जेक्ट्स आपने पढ़ाया तो we'll have this sigma yy, sorry, sigma xy, sigma yx and sigma yy. Normally जिन components में both this suffixes are not equal, इसको हम बोलते हैं कि shear stresses. So tau xy and tau yx both are equal anyway. So now this, if you see, this is called stress tensor. एंड आप सबको ये वैल्यूज पता है कि सिग्मा 1 कामा सिग्मा 2 ये बोलता है कि हम प्रिंसिपल स्ट्रेसेस, तो इसको बोलता है कि प्रिंसिपल स्ट्रेसेस. एंड अगर आपने इसका फॉर्मूला चेक किया तो क्या होता है, सिग्मा xx प्लस सिग्मा yy बाई 2 प्लस और माइनस स्क्वायर रूट ऑफ सिग्मा xx माइनस सिग्मा yy बाई 2 होल स्क्वायर प्लस सिग्मा xy और सिग्मा yx स्क्वायर एक्चुअली हियर. सो when you take plus sign आपको एक वैल्यू आएगा and with minus sign आपको दूसरा वैल्यू आ जाएगा. Okay, and these two values whatever you calculate, sigma 1 comma sigma 2, if you calculate, these are called eigen values of stress tensor. तो अगर आपने इस मैट्रिक्स के आपने आइगन वैल्यूज कैलकुलेट किया तो वो आइगन वैल्यूज आर नथिंग बट दिस प्रिंसिपल स्ट्रेसेस. ओके, सो आइगन वैल्यूज ऑफ स्ट्रेस टेंसर are principal stresses. Principal stresses. If you take an example, मैंने symmetric matrix इसलिए लिया था 1 2 2 1. So when you do this, you came to know that eigen values are -1 comma 3. Okay, आपने सॉल्व किया था इस इक्वेशन को, देखिए. So -1 comma 3 are the eigen values. अगर आपने इस मैट्रिक्स को, because this can be taken as a stress tensor, these two are equal, आपने अगर इस मैट्रिक्स को ये फॉर्मूला अप्लाई करके प्रिंसिपल स्ट्रेसेस कैलकुलेट किया तो sigma 1 is equal to sigma xx plus sigma yy by 2 plus root of sigma xx minus sigma yy by 2 whole square plus tau xy square. Okay, so 2 square. So you can see this sigma 1 is equal to 1 by 2 plus 2. So this is 1 plus root of this 1 square, this is 0 plus square root of 2 square is 2 square is 4 actually here. Okay, so this value is 3. So sigma 1 is equal to 3, maybe megapascals or whatever the units. Sigma 2, minimum principal stress, sigma xx plus sigma yy by 2. So 1 plus 1 by 2 plus root of, sorry, minus, यहाँ minus root of sigma x minus sigma yy by 2 whole square plus 2 square. So if you calculate this value, 1 minus 1 minus root 4 is 2. So this is equal to minus 1. So sigma 2 is equal to minus 1 actually here. So these are principal stresses, maximum and minimum principal stress, and they are nothing but the eigenvalues of this matrix जिसको आपने ऑलरेडी कैलकुलेट किया था. सो 3 कामा माइनस 1. एंड ये आइगन वैल्यूज एंड आइगन वेक्टर्स बहुत इंपॉर्टेंट चीज है जो आपने वाइब्रेशंस डील किया तो मल्टी वेरिएबल मल्टी डिग्री ऑफ फ्रीडम सिस्टम्स. इफ यू टेक फॉर एग्जांपल, आई वुड लाइक टू शो हियर, if this is a mass of m1 and if this is a mass m2, if you have some system like this, okay, multi degrees of freedom, then definitely you have stiffness matrix times this ax is equal to minus omega square into x actually here. Okay, so this is how you get the solution, and normally this lambda is actually given by omega square, and of course if you take magnitudes, and also omega is equal to mod omega is equal to magnitude of root lambda is what you will get. Okay, so ऐसे हम आइगन वैल्यूज को फ्रीक्वेंसीज कैलकुलेट करने में स्ट्रेस टेंसर्स में बहुत सारे लोकेशंस पे यूज करते हैं. ओके, सो एनीवे मेनी ऑफ यू नो हाउ टू कैलकुलेट दिस, हाउ टू अप्लाई दिस इक्वेशंस एंड कैलकुलेट द आइगन वेक्टर्स, लेकिन इसका मतलब क्या होता है, सो that we'll get to know from this diagram. Similarly, when lambda equal to minus 1 क्या होता है, so along the same line you'll have the vectors but with different direction or with different magnitudes and all. Okay, so that's what we'll get. So ऐसे हम eigen values and eigen vectors को calculate करते हैं. So I hope this video has helped you in understanding the concepts of eigen values and eigen vectors. We'll meet soon with some of the most interesting videos on fluid mechanics and all other subjects as well. Thank you all. Take care.